last topic we'll look in integration is applications integrals to kinematics. We've already seen this in the derivative direction. Remember, where displacement's derivative was velocity, velocity's derivative was acceleration. So now with integration, we get introduced as going backwards. Acceleration, back to velocity, back to displacement. And you will get questions that now can say, hey, why don't we start with this? Why don't we start with velocity and you can work both directions? Or you could start with acceleration and you could work all the way back to displacement. So we can now solve all sorts of physics questions just using simple calculus instead of relying on pages and pages of physics formulas. So we're going to sort of do physics sort of from the raw, just calculus perspective, rather than, not that the formulas in physics are bad, but it just, this is like, well, it all makes sense working this way. Oh, I'm going to switch back to my other notes that are blank. It's more fun to write. There we go. So what these questions really get back to is something that we did early on in our integration units. Remember when we did the solving for C questions? Where when you integrate, there's always a plus C, but if you want to find that C value, you need some additional information. And almost all of these kinematic questions work that way. Here they say, here's the acceleration. It's t plus 1. Find an equation for velocity. So if you're thinking, we are moving from acceleration back to velocity, so we are going to have to integrate. So to find velocity, it will just be the integral of acceleration, which was t plus 1 dt. And then we're given some information. Okay, it says find the equation for the velocity and the displacement given that s equals 0 and v equals 8 when t equals 0. So I'm going to just write a note here. When t equals 0, v is equal to 8. And when t equals 0, s is equal to 0. So what they're really giving us in this equation is an initial velocity and an initial displacement. Initial velocity, initial displacement is always when time is 0. It's where you began. So at time equals 0, this object has a velocity of 8. We don't know any, oh yeah, meters per second. Good. We can add those units in because they were given in the question. So integrating this, we would get t squared over 2 plus t plus c would be our velocity. And since we know when time is 0 that velocity is 8, we can plug in 8 for velocity, 0 for t, and solve that c is equal to 8. So our velocity equation is t squared over 2 plus t plus 8. That's our velocity equation. So we had to solve for c in order to figure that out. And the question is also asking us to find our displacement equation. That's just going to be the integral That's just the integral of velocity. Add 1 to the exponent and divide. Add 1 to the exponent and divide. And I'm going to use d this time because we're in the same question and we already used c. So we were told that when time is 0, displacement is 0. This was really nice of me, mathematically, to use 0 so nicely. And you'd find out that d is equal to 0, so your final displacement equation is just equal to this. So the idea is just knowing where you're starting. In this case, they're giving us a velocity equation. Find the acceleration. Well, that would be a derivative. So I can say that acceleration is equal to v prime of t, which in this case would be negative 10t. That's our acceleration in terms of t. Nope, there's no t there. Nicely derivative. The t would not be there. Minus 10 meters per second squared. Can you see that this is sort of looking like a rounded gravity question? When you have acceleration close to 9.8, but you don't want to do math with decimals, you use 10. Right? How significantly different would that make our lives? Like you jump off something, you just get to the ground a little bit quicker, right? But what would that do? Like if you tried to run 100 meters and gravity was negative 9.8, if you increase gravity to negative 10, would you be slower in running? I kind of think so. Because if I imagine gravity being really heavy, as soon as you lift that yourself up in the air, you come crushing right back down. So, interesting. Now, if the initial displacement, so they're telling us when t is equal to 0, s is equal to 40 meters, find an expression for s in terms of t. This time, we can start with our velocity and go up. So we're going to need to integrate. And if you integrate, you're going to get a plus c. But we know that initially, when time is 0, the displacement is 40. So that makes your displacement equation 50 by and I find gravity questions, especially when you get the displacement equation, quite telling. For one, if it's a gravity question, what this is really modeling is like throwing a ball up in the air. If you throw a ball up in the air, it will go up in the air and it will come back, right? Gravity never plays tricks. It's never that you're like, oh, I threw it up and it just kept going, right? It'd be wonderful for Olympics in a shot put. You're like, everybody else is just like there, and you're just like, whoa, there it goes. Have fun measuring that one. Yes, so they always make a parabola, because you throw a ball up in the air, it comes back down, okay? The value in front of the t squared if you take the derivative twice as always your acceleration, this number should be negative 4.9. Negative 5 when we want to make our math easier, okay? If you're using feet per second, I think acceleration in the US is negative 32. And so this will often be, in some questions, you'll see that a gravity question will have 16 at the beginning. They don't tell you the units, but it's like, oh, they're using different units so they can create different questions. This number is always your initial velocity. Because if we think about our velocity equation that was here, which was 50 minus 10t, if you plug in 0 per time, you will get just that 50. And so your displacement equation always has an initial velocity, right? So in grade 11, I'd see a question, I'd be like, I know how fast they threw it up in the air to begin with. You'd be like, how do you see that? Well, that value is there. And of course, this is always your initial displacement. So this ball, a person's on some sort of cliff 40 meters above the ground. And they're throwing it up in the air with an initial velocity of 50. All right, one for you to try. Let's see how you did. Working up from acceleration would have given you velocity, and then initial velocity of 3 when time is 0, solves for C. Next, we want a displacement, so we would integrate again. In this one, since it's a part B, wow, there we go. Since it's part B, it's not wrong. If you did plus C in this one as part B, I would be okay. But since it's all in the same kind of question, I did use a plus D. And then when is the particle at rest? If a particle is at rest, that means its velocity is 0. So plugging in 0 into the velocity equation, and this is probably what can sometimes make kinematics a little bit more difficult, is now you have 3 equations. Which equation should I use? Well, you just have to sort of think, what in the context, what are we talking about? We're talking about velocity, so I'd use my velocity equation. Time is 3 seconds and 1 second, and then what is the displacement at these times? Now we're going to plug in t equals 1 and t equals 3 into your displacement equation and find out the answers from that. Okay.